So first, an academic disclaimer. I am not a credentialed historian. I do have a college degree, but it's not in the humanities. But I'm a, sorry, I'm a history buff who is well read and curious, and I've read a lot of science histories and science non-histories. And I've made every effort to ensure the information contained in this presentation is historically accurate, but I've not read every book that I'm going to talk about, although I have read several of the books I'm going to talk about. So we'll start with a quote from Carl Sagan, one of my personal heroes, who said shortly before he died, one of his final quotes, "We've arranged a society based on science and technology in which no one understands anything about science and technology. And this combustible mixture of ignorance and power, sooner or later, is going to blow up in our faces. Who is running the science and technology in a democracy if people don't know anything about it?" So hopefully this presentation will help to, spread some of that knowledge. So I've got 3 parts of this presentation. First, we're going to talk about the methods of science and how it works. Then we're going to talk about the evolution of science and how it was developed over the millennium, actually. And finally, we're going to talk about science denial, which is, of course, an increasing problem in our modern times. All right, first, the methods of science. So the word science comes from the Latin word scientia, which means knowledge or understanding. Science is a systematic way to gain knowledge of the natural world. And in the Western tradition, scientists were originally called natural philosophers because, like the followers of a philosophical school, scientists adhere to a core set of principles, methodologies, and guidelines which allowed the secrets of the natural world to be unlocked. And these would become known as the scientific method. So the philosophy of science assumes that the natural world works according to repeatable physical laws that can be discovered through experiment. The scientific method begins with the observation of an unexplained natural phenomenon. And then a specific question about that phenomenon is formulated. And then next, a hypothesis is devised to answer the question that you've asked about that phenomenon. You then devise experiments to test your hypothesis and analyze those results. And the end conclusion of your experiments may lead to the hypothesis being discarded, or it might lead to it being further refined with additional applications of the scientific method. So let's talk about the difference between scientific theories and laws. If a hypothesis is confirmed through many repeatable experiments conducted by many scientists, then they can graduate to become a scientific law or theory. So scientific laws explain what happens. Some examples are Newton's law of gravity, which explains exactly how gravity influences the motion of objects, but it doesn't really explain why gravity works. The ideal gas law, which shows how the pressure, volume, and temperature of a gas are related to each other mathematically. Or the law of conservation of energy, which states that energy can't be created or destroyed, only change form or be transmitted. On the other hand, scientific theories explain why something happens. And examples of that include the Big Bang theory of the origin of the universe, that explains why the universe is expanding, has a uniform background radiation that was first detected in the 1960s, and contains the observed abundances of hydrogen and helium. All of those things are explained by the Big Bang theory. There's also the theory of evolution by natural selection, which explains how the diversity of life on Earth and the fossils in the fossil record came to exist. And then a more modern one is dark matter theory, or lambda-cold dark matter theory, which explains mainly the existence of spiral galaxies, which actually shouldn't exist based on a straightforward application of Newton or Einstein's gravity. So many people outside the scientific community mistakenly believe that applying the word theory to a scientific idea indicates that it's somehow maybe less trusted than if that idea were a law. But in science, both terms actually carry the same weight in terms of trust or truth. These terms only differ in that laws are successful hypotheses for what happens, while theories are successful hypotheses for why things happen. That being said, no scientific law or theory is sacred and unchangeable. Unlike other methods of knowing, like intuition, introspection, or the acceptance of religious truth, science is self-correcting because both laws and theories can be changed and challenged if sufficient evidence against them is found. Speaking of which, here are some abandoned scientific ideas. This is just a selected list of scientific laws or theories that were accepted at one time, but we don't believe these anymore. First, we got Ptolemy's law of refraction, which the Roman scientist or thinker, really, they didn't really have scientists back then. Ptolemy proposed this in year 150, but it was found to not really be accurate except for small angles of refraction and was superseded by what's called Snell's law in 1637. There's the phlogiston theory of combustion, which was proposed in 1667 and then abandoned about 100 years later after Lavoisier discovered oxygen, and that just proved to be a better explanation for the processes of fire. There's Bode's law of planetary distribution, which was proposed in 1772 because people noticed that there was an interesting resonance in the distance of planets from the sun, and people thought that that would just continue to hold, but the discovery of Neptune proved that the law was wrong. There was the miasma theory of disease, which was first proposed in antiquity. It basically said that disease is the result of bad vapors in the air. And this has, of course, been superseded by the germ theory of disease. Newton's law of gravity, which was proposed in 1687, very, we managed to send people to the moon with Newton's law of gravity, but it's not 100% accurate. It's subtly incorrect or incomplete in conditions where there is, intense gravitational attraction. So it's been superseded by Einstein's general relativity in 1906. And then finally, there's the theory of the luminiferous ether, which was proposed by Newton to explain how light waves can pass through empty space. When it was proposed, there was no way to test it, but they did have a way to test it by 1886, and they didn't find it. Einstein's general relativity provided an alternate explanation in 1906. So again, science is a self-correcting process. So scientific laws and theories which have stood the test of time and have few competitors, like the law of conservation of energy or the theory of evolution, are more likely to approach truth than newer theories like string theory or dark energy, dark matter, which, could be true, but they haven't been around as long as these more tried and tested scientific ideas. So here we have two quotes that I sort of like to kind of contrast these. One comes from the biologist Theodosius Dobzhansky, who said, "Nothing in biology makes sense except in the light of evolution." And then here on the right, you have a very recent quote from a Nature article that just came out as I was doing research for this presentation, where Antonia Seifert has come up with a new scientific finding that did make some news about how perhaps dark energy, we've been misinterpreting it, that it might just be the result of time dilation of light waves passing through emptier regions of space versus less empty regions of space. So again, things that are sort of at the cutting edge of science may be subject to being falsified by new findings, but things that are more tried and true, where there have already been a number of efforts to displace it, probably are closer to approximating truth. And this doesn't mean that newer ideas can't become more solidly truthful as time goes on. It's just that they need that level of rigor of people to do these experiments, to find these alternate ideas, so that we can find out where the real truth is. All right. So the scientific method was perfected in the 17th century and has done an amazing job of revealing the hidden laws of nature ever since. We owe virtually everything we know about physics, chemistry, and biology, as well as all the technology we built on top of all of those sciences, to the slow, painstaking, and occasionally error-prone, but self-correcting, application of the scientific method over the last 400 years. But there are limitations to science. Science has been very successful, but it's not perfect. In the 18th century, the highly influential philosopher David Hume worried the scientific method may actually not sit on solid logical principles. Since that time, other scientists and philosophers have found other concerns about the methods of science that I'm going to sum up in the next several slides. But some of the general principle or general questions, like what should be included or excluded from science? Like Hume asked, is the scientific method itself based on sound logical principles? Can the scientific method be applied in biased ways? And can science say anything about ethics or the supernatural? So first, let's talk about things that maybe aren't science, and we'll start by talking about pseudoscience. So pseudoscience is a field of study which tries to appear to be scientific, but whose proponents don't actually use the scientific method to justify their claims. Fields that are generally considered to be pseudosciences include astrology, the idea that stars influence current events; eugenics, the idea that science can justify theories of racial superiority; homeopathy, the idea that water can remember what was formerly in it after being severely diluted; creationism, the idea that God created humans and animals in their current form; phrenology, the idea that the size and shape of the skull can predict human behavior; and chiropractors. Yes, chiropractic is not actually a branch of medicine. The methods of chiropractors are not taught by real medical schools and are not really subject to scientific scrutiny. There's some debate about how to separate pseudoscience from science, but generally, a pseudoscience will make claims that are hard to scientifically test, will oppose investigation by outside scientists, and will show a lack of progress compared to a real science. In the 20th century, the Austrian philosopher Karl Popper tried to define more precisely what matters science can and cannot be applied to. He argued that science can only be applied to hypotheses that are falsifiable, meaning that it's possible to devise an experiment which has an outcome that could potentially disprove the hypothesis. According to Popper, any hypothesis that can't be falsified, that you can't devise an experiment for, is actually unscientific. Despite this, sometimes a hypothesis rings true, but no current technology exists to conduct the necessary falsification experiment. Such a hypothesis can even be accepted as theory, despite the lack of any experimental proof existing yet. Both the luminiferous ether and today's string theories can be considered unscientific by Popper's definition. And also, sometimes an untestable hypothesis is promoted to theory because the mathematics make it seem correct. This is especially true for modern string theories that claim that subatomic particles are actually strings that vibrate inside dimensions so small that we can't detect them by experiment. Different string theories require differing numbers of extra dimensions due to the differences in the different mathematical models behind different string theories. But without an experiment to ground such theories in reality, it's actually quite difficult to determine whether one string theory is more true or less true than another. And this is my opinion, but my opinion is that this is a main reason the string theory hasn't really progressed much since there was a lot of hype about it in the 90s. All right, let's talk about what David Hume had to say about science. So the way to design a hypothesis for a natural law is to describe future behavior based on past behavior. The use of past behavior to predict future behavior is called inductive reasoning. But the philosopher David Hume called into question the entire validity of inductive reasoning. He pointed out that it rests on an assumption that nature is forever uniform, and the future will always behave like the past. And he argued that that's really not reasoning at all, but rather just imagination, as he put it, to think that effects which have been measured repeatedly will always continue to happen. He also argued that it's invalid to assume that two events which happen repeatedly in a sequence are a case of the first event causing the second, saying that that also requires a similar leap of imagination. And philosophers of science were pretty troubled about this for about 150 years. But in 1903, the American mathematician Charles Sanders Peirce argued the scientific method actually doesn't use inductive reasoning the way that Hume described it, but instead, the skill to create a successful hypothesis is something he called abductive reasoning. According to Peirce, abductive reasoning is similar to deductive reasoning, which is the idea that you can prove that A caused B with enough evidence. But instead of starting with A, in abductive reasoning, you start with B and trying to figure out which A's could have resulted in B. This may allow for multiple possibilities for A, so it isn't as definitive as deductive reasoning, but it's much more logically grounded than just pure induction. And usually there's only a finite set of things that can really cause B, especially if your experiments are precise enough. So this was required reading for me in college. I do have a tech degree. The American historian Thomas Kuhn wrote this landmark book in 1963, The Structure of Scientific Revolutions, in which he pointed out that prevailing scientific paradigms can create bias that prevents scientists from accepting new findings. A paradigm, according to him, is a set of related ideas that are accepted by a majority of scientists in a given field. And he argued that scientists as a whole tend to oppose scientific findings which don't fit the established paradigm, and will go to great lengths to make problematic experimental findings fit established paradigms using clunky and complicated theories. Kuhn argued that there have been occasional scientific revolutions, like, for instance, the heliocentric revolution, where we came to the realization that the Earth goes around the sun and not vice versa. In which the established paradigms are abandoned because of overwhelming evidence that they're being incorrect. Kuhn also argued that an established scientific theory really can only be falsified when there's a new theory ready in the wings to replace it. Otherwise, scientists will continue to cling to the old theory even if evidence begins to stack up against it. So this just has to do with the biases of science. And as a scientist, one should be aware of the fact that you can fall into this kind of thinking. And that's why when I trained in the computer sciences, I was asked to read this book and kind of ponder on it. So also, science requires an unbiased freedom of inquiry. The scientist and historian Timothy Ferris argued in The Science of Liberty, which is actually in our library back there, that science cannot work if the scientific inquiry is hamstrung by political or cultural biases. One example he cited was the Soviet Union's embrace of something called Lysenkoism during the 30s. Lysenkoism was a pseudoscience that rejected both Mendelian genetic inheritance as well as Darwinian evolution by natural selection. These ideas are both rejected on the grounds that they were anti-communist because they denied the primacy of the collective over the individual. Instead, they felt like they wanted to believe in a Lamarckian-style evolution where the community can will themselves to evolve in a certain way. But your biases and your desires don't translate into what's really true, right? Unfortunately, Soviet scientists who would not reject Darwin and Mendel were sent to the Gulag. Due to this, Soviet scientists tried in vain to improve crop yields without using techniques based on artificial selection like the rest of Western civilization. And the Soviets would eventually realize their mistake and abandoned Lysenkoism in the 1960s. Let's talk about science and ethics. So science can only reveal what nature does and why nature behaves in those ways. It does not make moral judgments about how nature itself works, such as the cruelty of survival of the fittest, which I know that my own father wanted to reject evolution because he didn't like that whole concept. But again, what you like doesn't translate into what's true. Or the capriciousness of meteorite impacts. What should we do with the knowledge that it reveals? Starting in the 20th century, also, science began to unlock technologies which were ethically troubling, such as ways to create weapons of mass destruction, clone human beings, tinker with the evolved genetic code of life on Earth, and how to create forms of computerized artificial intelligence. It might be unethical to use some of this knowledge in certain ways, or at all, but these are very human judgments to make, and science, unfortunately, offers no guidance. Many argue also that science can say nothing about the supernatural because it's literally beyond nature. That's what supernatural means. But the American scientist Victor Stenger argued in the book God, the Failed Hypothesis, which I highly recommend, that the cumulative results of science actually have a lot to say about the supernatural. So for one thing, the success of science proves that the universe is, as assumed, governed by repeatable and unchanging laws. In addition to that assumption, science also asserts that if supernatural forces have influence upon nature, then such influence must be detectable by scientific experiment. But to date, no experiments have revealed the influence of supernatural forces upon nature, and that's not for the lack of trying. There have been failed experiments to find the weight of the soul leaving the body at death, or to measure the effectiveness of prayer, and none of these have yielded any supernatural findings. The unchanging behavior of the universe's physical laws also imply that no God with a decision-making consciousness is actively manipulating the universe, since these laws never vary from their unchanging principles without exception. Additionally, the findings of science regarding the vast age of the Earth, as indicated by geology, paleontology, and astrophysics, as well as overwhelming evidence from biology and paleontology, that all life, including humans, evolved from a single common ancestor through a process of natural selection, rather than being divinely designed special creations of God, contradicts the sacred scriptures of many world religions. In short, Victor Stenger said that what we see in nature as revealed through science is exactly what we would expect to see if there was no God pulling strings. All right, let's talk about the evolution of science. How do we get here? How do we learn how to learn, essentially? So in the time before science, everything was explained in terms of the supernatural. The gods brought the rain, seasons, and fertility. Magic was thought to be used to both create and cure sickness. And natural events like the appearance of a comet could be an omen of the future. The earliest thing that we could really consider to be any kind of empirical science really dates back to the Egyptians. Picture here is something called the Ebers Papyrus, which has been dated to 1600 BCE. It contains medical instructions, including methods for how to set broken bones, recipes for medicines, and advice for treating a range of bodily diseases and conditions, all based on presumably empirical findings. Even before this, the Egyptians had developed a numbering system by 3000 BCE, as well as a system of geometry that allowed for land surveys. The ancient Babylonians were the first people to record astronomical observations using their cuneiform writing system, and you can see this is an actual astronomical chart that's depicted here. They also invented the concept of the mathematical degree that we still use to position astronomical bodies, or even bodies on the surface of the Earth, still also measured in degrees. By the 7th century BCE, they had developed mathematical models to predict the timing of eclipses, as well as the motion of the planets Mercury and Venus. And they noticed that Mercury was always within 22 degrees of the sun. The Babylonian definition of the solar year and lunar month are still used by astronomers today. And our modern astrology also finds its roots in Babylonia. Babylonian astronomy was far from scientific as we would consider it, because a form of astrology which was used to foretell good or bad omens was pretty much always interwoven with the astronomical observations that were made. All right, let's talk about ancient India. At around the same time as the Babylonians, the ascetic philosopher Sanjaya Balataputta founded the so-called heretical Indian philosophical school called Ajnana. He based his philosophy around the logical construct called the Caduskoti, which is the idea that for any logical proposition X, the truth has to be one of these four things. Either it's X, or it's not X, or it's both X and not X, or it's neither X nor not X. So pretty much anything that you would propose has to fit into one of those four buckets. So Balataputta applied this construct to supernatural questions and took the agnostic position that answers to supernatural questions were unknowable, which is actually very similar to the creation hymn of the Rig Veda, which is written around 1900 to 1200 BCE, which ponders the creation of the universe. So here is the end of that creation hymn. But after all, who knows, and who can say whence it came and how creation happened? The gods themselves are later than creation, so who knows truly whence it has arisen? Whence this creation has arisen? Perhaps it formed itself, perhaps it did not. The Creator looks down on it in highest heaven. Only He knows, or perhaps He does not know. So again, this is very similar to the logical construct here, and the actual hymn from Rig Veda sort of influenced this logical idea. Around the same time in India, there was another school of learning that emerged called Anvashiki. Anvashiki roughly translates to investigative reflective inquiry, and was expounded upon by several early Indian philosophers. Charvaka, also known as Lokiata, was one of the popular varieties of this school, a philosophy that urged care and skepticism in all deductions. Charvaka teaches, for instance, that one should not jump to conclusions about things, such as assuming fire when seeing smoke in the distance, as smoke may be the result of other causes. It also teaches that perception is the only path to knowledge, rejecting other paths such as intuition, logic, and received knowledge. To the disciples of Charvaka, perception meant what is revealed by the senses or direct human experience. The Charvaka school was also explicitly atheistic, rejecting core Hindu concepts like the multitude of gods, reincarnation, karma, and religious rituals. And so here's a quotation related to this that comes from a summary of the major schools of Indian philosophy written in the 14th century. And when talking about Charvaka, he summed it up: there is no world other than this, there is no heaven and no hell. The realm of Shiva and like regions are fabricated by imposters. All right. Let's move on to the early Greek proto-scientists. And this is also in the same period. Like the 7th century BCE was apparently a very fertile period for thinking rational thought, because in Babylonia, India, and Greece, we find the first real semi-modern thinkers, I guess you could say. Some early Greek proto-scientists include Thales of Miletus. He was one of the first people to seek natural explanations for natural phenomenon. He proclaimed that all things have a natural cause, although he also proclaimed that all things are full of gods, leaving room for the supernatural. And then there's Pythagoras of Samos. You've probably heard of him. He was one of the first Greeks to study math and logic for its own sake. He famously discovered the geometric Pythagorean theorem and may have been the first person to realize that the world is round. Also, Heraclitus of Ephesus, who lived about a century later in the 6th century BCE. He wrote about something called the Logos, or the natural order of the universe. So here we have sort of the first person sort of suggesting that there is a natural order to the universe that we need to unlock. He believed it contained eternal truths that humans were generally ignorant to, as if they were asleep. He believed all was in flux, and he's most famous for saying that you can never step in the same river twice, because it's not the same water each time you step in. Ancient Greek logic was also the first to use logical proofs, which are sequences of logical statements designed to prove a mathematical or logical conjecture. These proofs begin with axioms that are considered to be true without need for further proof, and which are used to build up the proof of the less obvious conjecture. So here we just have a use of axioms to prove that an angle has a certain number of degrees based on accepted geometric axioms. So Socrates of Athens is really one of the first people to really set the Western civilization at least forward in terms of logical thinking. He was born into wealth around the year 470 BCE. After serving in the Peloponnesian War, he decided to dedicate his life to becoming a thinker and teacher. His influence would be so great that Greek thinkers before him are called pre-Socratic. And he was one of the first Western thinkers to stress the importance of deductive reasoning. He invented something called the Socratic method of asking questions to gain knowledge through deductive reasoning. So here's the Socratic method. So I would say that, we have this modern scientific method that we talked about earlier. This is one of the first sort of methods that was devised by anyone to get to truth. The first step in the Socratic method is to define a thesis or a statement to be proved or refuted. Then the next step is to have debaters engage in dialogue, each one taking opposing sides of the truth of the thesis. The purpose of the dialogue is to find and ask questions related to that thesis that reveal factors that had not been considered by the other debater that he must agree to due to reason. And then the end state of the Socratic dialogue is reached when one debater reaches something called aporia, or which is Greek for puzzlement, upon realizing the statements that they've agreed to during the dialogue have undermined their support or opposition to the thesis. So the Socratic method was not really science as we know it, but it was a systematic process. Socrates believed it was important for a person to realize their level of ignorance as part of the undertaking of a path to knowledge. Ignorance could take the form of questions never considered, received ideas never challenged, or natural assumptions that were just never thought through. Next we get to Plato. Plato was a student of Socrates whose ideas about knowledge and logic would dominate the West for over 2,000 years. He founded the Philosophical Academy at Athens, which was dedicated to the ideas of his mentor Socrates. He cast himself as one of the most astute followers of Socrates, and in fact, Socrates didn't really write anything himself. Everything we know about Socrates comes from things that Plato wrote. Plato's biggest contribution of his own to reasoning and logic was the concept of perfect forms. He argued, based on the teachings of Socrates, that you cannot discern knowledge through experience alone. Instead, Plato thought that your senses reveal individual imperfect forms of potentially more perfect concepts. He thought the Socratic method could be applied to tease out those higher forms of those concepts that we experience, and eventually those perfect forms can be deduced to their logical attributes and used for logical reasoning. So Plato's perfect forms may have seemed like a step forward in the quest for reason and logic, But Plato argued that any perfect form we can conceive of in our mind's eye must really exist somewhere, meaning that according to his perfect form concept, God must exist because we're able to conceive of such a perfect form of a deity. Next, we have Aristotle. Aristotle studied under Plato at the academy. So again, Socrates knew Plato, who knew Aristotle. Plato recognized his genius and once named him the mind of the school. He wrote a landmark set of books on logic titled the Organon around the year 350 BCE. In it, he expanded the concept of logic beyond pure mathematics or geometry to include something called syllogisms. Syllogisms are logical statements that can be combined to create proofs that follow from general statements that are believed to be true. So here we have a simple syllogism. To construct one, we take a statement generally believed to be true, which is called a major premise. Then you use it to draw a conclusion about a more specific statement linked to the major premise, which is called the minor premise. So in this example, all cars have wheels would be the major premise. A Honda Civic is a car. Therefore, a Honda Civic has wheels. So syllogisms can suffer from a number of logical fallacies. Aristotle and others after him studied the logical conclusions that could be drawn from syllogisms and found a myriad of ways to create faulty syllogisms that don't actually reveal truth. Aristotle himself identified all these that are on the right, and there have been more that have been identified since Aristotle. Additionally, a syllogism can only be as true as its major premise. If you start out with a major premise that has flaws, then obviously any conclusions you draw from it are also going to be flawed. So Aristotle argued that syllogisms could be used to answer questions about the natural world, such as what natural things exist, what the details of those things are, and why those details are the way that they are. He believed that you did need to use inductive reasoning at the start of knowledge, but that truly understanding scientific truths required answering the why questions, and he believed that was only possible using deductive reasoning through syllogisms. So here's a quote from Aristotle that comes out of one of his books that was part of the Organon. We suppose ourselves to possess unqualified scientific knowledge of a thing, as opposed to knowing it in the accidental way that a sophist knows, when we think we know the cause on which the fact depends, and that is the cause of that fact and no other, and further, that fact could not be other than it is. So he's basically arguing that you need to have a complete knowledge of a thing before you can really say anything about it. And this would become a major point of debate among early scientists later. So the logical approaches of Socrates, Plato, and Aristotle were arguably the closest the ancient world came to modern science. Even as the Dark Ages descended upon Europe at the end of antiquity, when the knowledge of the ancients was mostly burned and destroyed, the knowledge of the Greeks is still preserved in the Middle East. Two of the best known thinkers of the Middle East that preserved this knowledge were a guy named Ibn al-Haytham, known as in the West as Al-Hazm, and Ibn Sina, who is known in the West as Avicenna. They preserved Greek methods of logic, and they both criticized Aristotle actually for being too dismissive of paths to knowledge outside of this whole syllogism concept. They felt that understanding nature required more emphasis on the value of inductive reasoning and on their ideas regarding experimentation. Middle-aged Europeans were reintroduced to these ideas from antiquity by that contact with the Middle East. Once that happened, most European thinkers in the early Renaissance, late Middle Ages, became as fascinated by syllogisms as the ancient Greek thinkers were. And the ideas of Plato and Aristotle were revered by those medieval thinkers as being close to perfect. So, jumping on the bandwagon in the 13th century, the Christian saint Thomas Aquinas developed his own set of syllogisms, which he called the five ways, which he claimed proved the existence of God. One of them can be found at Reindt, which he called the argument from degree. So it starts, there's a gradation to be found in all things, where some things are more good than others. Things can be compared in proportion to how closely they resemble that which is the most good. Therefore, if there is nothing that is the most good, then there can be nothing that is good at all. It follows, therefore, that if anything is good, there must be something that is the most good. So I would argue that these first four probably do follow logically. I mean, if something is good, that means that if it's the only good thing, it has to be the most good. The problem is that there's an irrelevant conclusion fallacy at the end here, which is one of the ones that Aristotle himself realized you could suffer from. That final conclusion is, therefore, there must be something which is the ultimate perfection, which we call God. But that's a biased definition of the most good thing, an assumption that it must be God-like. Perhaps it could be something far less supernatural, like just human compassion being the most good thing, right? In that same century, the 13th, some controversies emerged where certain aspects of Aristotle's teachings, which are becoming more widely disseminated, were declared to be in opposition to Catholic dogma. Between 1210 and 1277, the Catholic Church issued a number of condemnations which banned the teaching of certain ideas regarding God and the natural world that came from Aristotle. Most of those ideas were related to Aristotle's concept of an aloof and distant God who acts as what he called unmoved prime mover. And for a time, the works of Aristotle were actually banned in Paris. And I didn't know that until I did this research. Some historians believe that these condemnations actually help promote the advancement of science by helping to knock Aristotle's ideas and methods off their pedestal of perceived perfection. So it's actually after this that we start to find the first medieval thinkers that attempted to move beyond these Greek ideas. In the 13th century, the proto-scientist Roger Bacon distinguished between knowledge derived from arguments, such as syllogisms, and knowledge derived from experiment, and stressed the importance of the latter. And then a century later, William of Ockham would introduce his famous Occam's razor, a methodology for choosing between potential explanations for a phenomenon, hypotheses. Occam said the simpler explanation is probably more correct. The first major scientific revolution after antiquity was the heliocentric revolution of the 16th century. Since antiquity, it had been assumed that the Earth was at the center of the universe, and the sun, because the sun and stars appear to move around the Earth during the day and the night. However, the motion of Mars, which can sometimes move forward and then back up and then move forward again if you measure it over several days, was always difficult to reconcile with this idea that the Earth is at the center of the universe. The ancient Roman thinker Ptolemy explained Mars by proposing that it had a second small orbit around the center point of its main orbit, something he called an epicycle. Again, going back to Kuhn and his book, this is one of these contrived things that people will put into scientific thinking because they're really trying to stay with the established paradigm. More precise measurements taken by 16th century scientists like Copernicus, Tycho Brahe, and Johann Kepler made it clear that only a model where the planets, including Earth, orbit the sun could actually explain the motion of Mars precisely. All right, so here we come to Francis Bacon, not to be confused with Roger Bacon 2 slides ago. The English nobleman Francis Bacon, who was the Lord Chancellor of the court of King James I, pondered science and philosophy and wrote a number of books that would have extremely great influence on what science would become. And he titled his book, by the way, Novum Organum, Organum being the name of Aristotle's book. So he's got the new hotness. So Francis Bacon attended Cambridge in his youth, but felt that the latest scientific thinking at that time, which is still mainly based on the ideas of Aristotle, was inadequate and had been shown to be prone to error. He argued truth could only be discerned through a precise and skeptical examination of the experiences that one has in nature, which is a philosophical view called empiricism. Bacon argued this method would be employed using a new method of induction not based on syllogisms, which he called the Baconian method. So here we have a quote from Mr. Bacon. There are and can only be two ways of investigating and discovering truth. The one rushes up from the sense and particulars to axioms of the highest generality, and from these principles and their indubitable truth, goes on to infer and discover middle axioms. And this is the way in current use. So that's the Aristotle's way of doing things. You have an observation, but you have to immediately go to some higher plane of thinking of perfect forms, and you can only really judge things based on that and not based on the actual thing that you saw. The other way draws axioms from the sense and particulars by climbing steadily and by degrees so that it reaches the ones of highest generality last of all. And this is the true, yet still untrodden way. So Bacon argued that inductive reasoning was necessary despite its potential flaws. He warned of human tendencies, which he called idols, that can result in erroneous conclusions. Among these are the idols of the tribe. Those are false ideas we get from human-centered thinking, like seeing perfection in perfect forms where none exist. Idols of the cave. These are false ideas we get from the peculiarities of our own childhood life experiences, even our personal likes and dislikes. Idols of the market. These are false ideas caused by erroneous shared understandings that many people have, which can be the result of erroneous ideas being made into words. Or idols of the theater. These are false ideas created by devotion to false or imperfect philosophies which cause us to reject our experience. So Bacon felt that hypotheses about natural phenomenon should follow from a careful examination of scenarios where a phenomenon is present or absent. Similarities between those scenarios should point to potential hypotheses about a phenomenon. So here is actually an example that we have from his new Organon book. So he wanted to consider the phenomenon of heat, and he suggested that a good way to do that would be to first try to look at where heat is present, and these are some of the suggestions that he had about where you define heat in places like the rays coming from the sun, meteors, thunderbolts, obviously fire, et cetera, et cetera. And then he also suggested that you should look at where the phenomenon is absent. And so, for instance, there's no heat coming from the moon or from stars, at least not as far as we can tell. Still liquids are not generally hot like boiling liquids are. Fresh horse dung might be warm, but old horse dung isn't. And living bodies are warm, but dead bodies are not. So based on kind of putting together some observations like this, you could make some potential hypotheses. So maybe a hypothesis could be that bright objects emit heat. Well, the moon and the stars are bright, but they don't seem to emit any heat. Boiling liquids they're not bright. So let's cross that one off the list. Then another idea might be that noisy objects emit heat. Well, you could say boiling liquids, fire, meteors, thunderbolts, they're definitely noisy. But, rays of the sun are not noisy. So let's cross that off the list. Then his final suggestion was, well, maybe objects in motion emit heat. Well, rays of the sun coming from the sun, they are in motion. Meteors are in motion. Thunderbolts are in motion. Fire is in motion. Boiling liquids. Fresh horse dung was recently in motion. And nothing is really contradicted in the where heat is absent column. So Bacon suggested that, a reasonable hypothesis might be that objects in motion emit heat. And that's actually kind of true, because of friction, things in motion can emit heat. But, arguably it's a bit accidental, this discovery by Francis Bacon, but this general idea that you should look at what's actually happening and observe it, and not just think about abstract concepts. This was really the key difference in what Bacon was saying, and the key reason why what he was saying was so important. All right, now let's come to René Descartes. So a few years after Bacon, the French thinker René Descartes, who famously said, "I think, therefore I am," also tried to put forward a new system for scientific inquiry that would replace syllogisms. He did so in two books written around the year 1640. Like Bacon, Descartes believed the methods developed in antiquity for obtaining knowledge were inadequate. He said they needed to be rethought from first principles. But, unlike Bacon, Descartes thought that humans actually can't trust what their senses tell them, and thus he thought that using inductive reasoning based on what the senses are telling you about natural phenomenon was just a fatally flawed idea. He argued instead the best way to understand the universe was to use pure reason applied starting with innate ideas through deduction alone. So actually, while Descartes thought that Aristotle was wrong, his own proposal on how to replace it wasn't really that different than what Aristotle was saying. So Descartes was a contemporary of Galileo, who famously became a major supporter of the heliocentric theory of the solar system as a result of the observations he made with early telescopes. According to Descartes, Galileo jumped to the conclusion of heliocentrism because he was using induction rather than deduction to arrive at his ideas. This is revealed in a letter he wrote to fellow scientist Martin Mersenne. Without having considered the first causes of nature, Galileo has merely looked for the explanations of a few particular events that he has thereby built without foundations. So Galileo was one of the first European scientists to use experimental models. He performed experiments with pendulums and inclined planes in order to formulate his own laws of motion in 1638. Those were later superseded by Newton's laws of motion. He is famously attested to have dropped two balls of differing weights from the Leaning Tower of Pisa in order to prove that they fall at the same rate, contrary to the teaching of Aristotle, who said that heavier objects fall at a faster rate. Galileo was careful to try to use reason, mathematics, and logic to back up his experimental results whenever possible, because again, at that time, that was really considered the preferred way to do things. For instance, he came up with thought experiments to demonstrate that if you tied two objects at different weights by a string and then dropped them, that would lead to some kind of paradox if Aristotle was right. Despite the objections of Aristotle and Descartes, increasing numbers of scientists after Galileo began to use experimental principles. In 1662, the scientist Robert Boyle, famous for his law of gases, helped to found the Royal Society of London, which still exists today, a scientific society that would promote the use of experimental methods. And that was actually the reason the Royal Society was founded, was to promote experimental methods. The philosopher Thomas Hobbes, who lived at that same time, was another thinker who, like Descartes, felt strongly that science needs to begin with deductive reasoning and not experiments. He attacked the creation of the Royal Society in his book Dialogus Physicus, where he warned that an experimental society was doomed to waste its time because they had no guidance from any kind of carefully reasoned principles. So this wouldn't really be settled until Newton. Newton was part of the next generation of scientists after Galileo. His masterwork, Principia Mathematica, outlined his theory of gravity and stood unchallenged for over 200 years. Later editions also included 4 rules for reasoning that he felt were important for making scientific discoveries. His rules for reasoning were based on using experiment, not reason deduction, as the primary tool for extracting knowledge from nature. Newton felt the use of reason should follow experiment, not come before, in the formulation of those hypotheses that may be imagined. This put Newton's ideas much more in line with the ideas of Francis Bacon than those of Descartes. The enormous success of Newton's theories, again found using experiment, settled the debate among most scientists about whether experimentation or reasoned general theories should come first. By the dawn of the 18th century, the debate about deduction versus experimentation had been settled. Much of the scientific method as we know it had been established and was beginning to yield the fruits of Enlightenment science. But the scientific method was still mostly an unwritten code of scientific culture. But in the early 19th century, the scientists John Herschel and William Whewell both wrote books intended to better define the scientific method and its best practices for the benefit of educating future scientists. Herschel argued the best hypotheses are those which tie together experiments in different fields to find what he called universal laws of nature. Whewell provided some loose guidelines for creating hypotheses, but argued that invention and genius were required to find the best ones. All right, and now we move on to the denial of science. Science denial is the rejection of the consensus findings of the scientific community on a particular topic by people outside that community. It's very different from the normal disagreements that scientists have when they vet competing theories before reaching consensus. Science denial dates back at least to the denial of heliocentrism in the 16th century. In that case, on the denier side, were scholars who believed that Greek thinking, which included the belief in geocentrism, was basically perfect and couldn't be improved upon, as well as clergy who argued that certain biblical passages, like the sun standing still in Joshua, or the earth cannot be moved in the Psalms, favored the geocentric universe. On the other side were proto-scientists who insisted that the data recorded from the observation of their telescopes absolutely proved heliocentrism, and who rejected the infallibility of Greek thinking and tread closely to rejecting the infallibility of Scripture, or at least the interpretation of those above verses as requiring a geocentric universe. The next big science denial is, of course, evolution. Evolution has been denied for more than 2 centuries because it denies the creation stories of major world religions, implies humans came from lower animals, and implies God didn't design humans or animals because natural selection was that guide. Even the majority of established scientists at the time Darwin debuted his evolutionary theory in 1859 refused to accept it because their reason was clouded by their religious bias. However, today, all serious biologists agree the fossil record contains overwhelming evidence of evolution, which has even been observed in action in microbes and fruit flies. And indeed, I love this quote, so I put it here again, nothing in biology makes sense except in the light of evolution. Besides evolution, there have been other scientific findings that have been denied since modern science has developed. Most of these have been contemporary controversies of the 20th and 21st centuries. So various times there have been people that have argued that all of these things are bogus. The dangers of lead exposure, the dangers of asbestos exposure. My dad was also not a believer in, he believed asbestos was safe. The dangers of tobacco and secondhand smoke, the theory that HIV causes AIDS, the safety and effectiveness of vaccines, the safety of fluoride in your water, the safety of genetically modified food, a human-caused climate change, human-caused depletion of the ozone layer, the effectiveness of alternative COVID treatments, and the theory that fracking can cause earthquakes. All of these things have been denied by somebody, or in many cases, groups of organized groups, mostly in the past 100 years. Science denialism is fueled by a strong desire not to believe the science, but the specific reasons for not wanting to believe the science may vary. Often, the denied scientific finding negatively impacts industries that are resistant to change, especially when that change negatively impacts them directly. Individuals can also be resistant to change their own personal habits due to science, and these are just some of the driving factors behind denialism of the dangers of things like lead, tobacco, CFCs, fracking, climate change. They all require an industry to make changes or require people to change their habits. Another major cause of science denial is a feeling of personal unease with a technology, possibly initially caused by some kind of disinformation, which can cause you to believe it's unsafe despite a scientific consensus of safety. This is the main driving factor behind denialism of the safety of things like fluoridated water, genetically modified food, and vaccines. So let's talk about vaccine denial. This one actually does date back to the first vaccines. You can see this very old cartoon. So increasing numbers of Americans are rejecting vaccinations due to the following reasons. Fear that vaccines can actually cause the disease, fears that vaccines cause other diseases like autism in children, and concerns about bodily autonomy. And like I just said, it's not new to oppose vaccines. The first opposition dates back to the invention of the first smallpox vaccine in the early 19th century. Many opposed vaccines back then for reasons 1 and 3 above. Autism wasn't really known back then. And also, many people were concerned that early vaccines, which tended to involve injecting tissue from infected people or animals, might render you unclean according to the rites of the Bible. So here are some metrics on vaccine hesitancy from the Institute for Health Metrics and Evaluation. This just shows a sample of people who were hesitant about getting a COVID vaccine in February 2022, and counties in red had more than 20% hesitancy. All right. Also, increasingly, the motivation for science denial can be a sense of political tribalism. One of the earliest examples of this was the denial of the theory that HIV causes AIDS. The struggle to scientifically unravel the cause of AIDS in the 80s was hindered by the view of some on the political right that AIDS was a divine punishment for a sinful lifestyle. Starting in 1987, the microbiologist Peter Duesberg, who was actually a member of the National Institutes of Health and a scientist, strenuously and repeatedly argued that AIDS was the result of drug use, poor diet, and other lifestyle choices, not HIV. More recently, during the 2020 COVID pandemic, many conservatives, starting with President Donald Trump himself, insisted that medicines like hydrochloroquine, which is an anti-malarial, and ivermectin, which is a dewormer, were effective treatments for COVID without any scientific evidence whatsoever. This evolved into a situation where conservatives began to trust medical disinformation and lose trust in scientifically backed effectiveness of the COVID vaccine that ended the pandemic. In 2016, Sean Otto, a novelist and the founder of a website called sciencedebate.org, which is intended to spark debate about government science policy, wrote a book that I would highly recommend, warning that certain political forces are seeking to undermine science. He defined these as a union on the political right of fundamentalist religious interests who have been uneasy with science since evolution, and businesses that don't want to respond to climate change or environmental concerns. He also argued the political left actually helps fuel some of this anti-science, ironically, by sometimes allowing truth to be relative, and sometimes siding with unscientific health or nutrition ideas, like the idea that vaccines cause autism or that GMO food is unsafe to eat, without actually following the science. More recently, just this year, Baylor University medical researcher and science media personality Peter Hotez wrote a book calling attention to the dangers of anti-science, particularly in the field of medicine. In addition to giving a harrowing personal account of being an outspoken supporter of medical science in the time of COVID, Hotez called out the dangers of the increased politicization of science by often right-leaning pseudo-intellectuals who dispute established scientific opinion with conspiratorial, not scientific ideas. Hotez, like Otto, argued that it is in the interest of certain political groups to foment anti-science in order to weaken regulations related to climate change, the environment, health, and safety. Here's a quote from Mr. Hotez. I don't even call it anti-vaccine misinformation or disinformation anymore. I call it anti-science aggression. These are not mom and pop groups we're up against. These are well-funded, well-organized political entities that are working to undermine the fundamental infrastructure of American science, and we have got to take a stand. In 2007, a law professor at UC Berkeley named Chris J. Hufnagel started a blog called Denialism, in which he identified several tactics which deniers of different sciences have in common. In 2013, John Cook, a behavioral science research fellow at the University of Melbourne, Australia, expanded on these ideas and coined an acronym called FLICK, basically saying that regardless of which science you're denying, chances are you're relying on fake experts, logical fallacies, maybe you're making impossible expectations about what the science says, you're cherry-picking results for things that favor your skewed worldview, or you just are believing in conspiracies. Also, a few years after that, Professor Matthew Hornsey of the University of Queensland, Australia, studied the reasons for science denial for decades and developed a tree model to explain the origins of anti-science attitudes. And so you can see here that things like you have a vested interest in a particular anti-scientific thing, or maybe you have a conspiratorial worldview. These things can manifest themselves as particular anti-science ideas. These are the major reasons uncovered by research studies designed to discover why individuals deny science. These would correspond to the roots in that tree model of denialism that we just saw. They include deeply held personal beliefs or ideologies. That might be your barrier to accepting evolution, for example. Maybe you've been exposed to disinformation and you believe that vaccines caused your child's autism. Maybe you believe that scientists involved in research into certain topics are part of some big conspiracy. Maybe you feel powerless or anxious in the case of troubling scientific findings like climate change. Maybe your political or social identity says that you have to believe a certain thing that's anti-science. Or maybe you're personally or professionally invested in something that's being called into question by science. In 2021, a philosopher at Boston University named Lee McIntyre communed with science deniers at such places as flat earth conventions and turned lessons he learned into a practical book on how to persuade science deniers. So he made 6 recommendations. Try to keep emotions out of the exchange. Discuss your differences but no personal attacks. Listen carefully and try to articulate the other position accurately. Show respect even if you think someone's ideas are crazy. Acknowledge that you understand why someone might hold the opinion that they have. And try to show how changing facts don't necessarily mean that you have to upend your entire worldview. And I'm going to leave this presentation last slide on a happier note, which is that it is actually possible to blunt the effects of science denial. There's actually been a scientific study on the effectiveness of challenging the misinformation given by science deniers. In 2019, 2 German researchers, Philipp Schmidt and Cornelia Betsch, performed an experiment where they tested 4 possible ways of rebutting science deniers and found that the worst thing you could do was to let false facts go unchallenged. They found that specifically debunking misinformation given by a science denier, as well as pointing out logical fallacies or conspiratorial thinking in the way a science denier draws their conclusions, could both be equally effective in preventing an audience from accepting anti-science disinformation. Many of these same researchers and authors have called for a better public understanding of how science works as another possible solution, both to explain how controversial science facts were determined and to better understand the public of how science works in general and the fact that it's not some big conspiracy, but just a systematic way to understand what is true. Public lack of this understanding is the same exact problem Carl Sagan noticed in 96 that was the start of this presentation. And hopefully, with more attention, it can be solved. And that's it.